This is our first topic for the review course, Machine Design. The title of this presentation is Materials and Specifications. For the contents, we'll first discuss the standards and specifications, how is it defined, and who are the governing authorities that establish these standards. After that, we will classify the materials. It's a general classification of the materials. Then after this would be a detailed discussions regarding the different types of materials. For example, the carbon steels, stainless steels, aluminums, and so on. Okay, so for the standards and specifications. Standards and specifications are documents that describe and or recommend a set of rules and conditions for how materials and products should be manufactured, defined, measured, or tested. Okay, so one description of standards is that we can say that standards, it's more on compatibility, right? So it says here that how materials and products should be manufactured. So if you have the same, let's say, method of manufacturing, then of course you can have a you can have a compatible condition. Okay, so defined, measured, or tested. Now, who are the ones that sets forth these standards? Now we have here some of the governing authorities or governing organizations that sets forth the standards and specifications related to the materials. Okay, so we have AISI, and that stands for American Iron and Steel Institute, the SAE, Society of Automotive Engineers. We also have ASTM, that's the American Society of Testing and Materials, and the UNS, Unified Numbering Systems, and the AA, that's the Aluminum Association. Now there are still many more standards, but these ones, they're actually you'll encounter this in the specifications or the designation of the materials. Okay, so for the classification of materials, we have already learned that the engineering materials can be classified into four types. We have the metals, ceramics, polymers, and composites. And for the metals, it is further subdivided into ferrous metals, which means it contains iron, and this one is non-ferrous. It just simply means that it does not contain iron. For the ceramics, we have this crystalline ceramics and then the glasses. For the polymers, we have thermoplastics, thermosets, and elastomers. Then lastly, the composites, which is just simply the combination of the three or any of the two above here, which produces a superior properties. Okay, let's talk about the carbon steels and its alloys. So we can say that carbon steels and its alloys, they're most common and they have a wide range of applications. The applications, for example, is the body of an automotive. Okay, so it's actually it is a carbon steel metal. Another one application is in the construction industries, like for example the bars, the I-beams, things like that, or the plates. So it can be said that they're actually the most common. So they're available in plate. Okay, this one. So it's plate or sheet if it has a thinner thickness, then strips, bars, wire tubes, castings, and forgings. Okay, so what is steel actually? Now, steel is an alloy. So when we say steel, it is a composition of iron and a carbon. So having a carbon content ranging from 0.15 to 1.7%. Now take note of this range because this range actually depends upon the references. So some says it's 0.3, others says the upper value is 2.0 or something. So this, I think these are just range that depends upon the references. Okay, and if we take a look at this diagram, we have an arrow line here at the bottom, which indicates the carbon content by weight. And if we have this range right here, let's say 0.15%, and then an upper range of 1.7%. Now, anything below 0.15% is termed as wrought iron, and anything in between 0.15 to 1.7 is termed as steel, and 1.7% and above, that's the cast iron. Okay, so again, this limiting values, they actually depends upon the references. Okay, now what's the effect if you add more carbon in the composition? So we can see here we have an arrow indicating the strength and an arrow indicating the ductility. Now for the strength, if you increase the carbon content, basically you are increasing the strength. You get, the steel gets more stronger. Okay, so here we have actually, let's say, a low carbon steel, and right here probably high carbon steel. So as you increase the carbon content, you're actually making your material stronger. But the downside is that the ductility gets lesser. When we say ductility, now when we say ductility, what that means is that it can be related to the deformation, or you can undergo plastic deformation. Okay, so there are applications wherein you don't want a ductile material, like for example the car body, the body of an automotive. That's actually or sometimes it's referred to as the dead carbon steel. Right, so it's sometimes referred to as the dead carbon steel, or the lowest possible steel that has, the steel that has the lowest possible carbon content. Okay, dead carbon steel, or sometimes low carbon steel. So if you have an application wherein you need more, let's say, forming, you want to form it, then of course you would want this type of steel. But if you need a stronger material and you don't have much concerns about the ductility, then you would want a high carbon content material. Okay, now for this classification of carbon steels and its alloy. So we have low carbon steel. In this first column, we have low carbon steel. We have medium carbon steel, high carbon steel, and some alloys right here with some additional elements. It says here containing sulfur and phosphorus. And we also have high strength low alloy steel, or HSLA. Now, what this means is that for a low carbon steel, you have maybe somewhere like right, maybe somewhere right here. Okay, again, I have to change my marker. So maybe somewhere here, that's the low low carbon steel. And then if you increase the carbon content, then maybe right here, then that's our medium carbon steel. And right here, probably you'll have a high carbon steel. Okay, so we have these characteristics again in terms of strength and ductility. And another thing right here is that if you increase the carbon content, you're actually making the material difficult to weld. Okay. With regard to the typical applications for the low carbon steels, we have machine components requiring ductility and not strength. Okay, for medium carbon steel, we have gears, axles, and connecting rods. So these are parts of the machine that actually requires more strength. Okay, and with this one, high carbon steel, we have the drills and cutting tools. So of course, when your application is about tools, or let's say drills and cutting tools, and then of course you don't want deformation, you don't want ductility. What you want is strength. And then there are still other types here of carbon steel alloys that contains other elements, just to improve the properties. So for example, this one, it says here improve machinability. Okay, and for HSLA, it says here same products as low carbon steel but with improved properties. Okay, now let's talk about the ASI and SAE designation for a carbon steel. It's basically the concept is that how do we classify, or how do we call, or what's the name of the material? Okay, so that's what a designation means. Okay, for the SAE classification system for alloy steels, it uses 4 or 5 digit number. Okay, so for example, we have here a 4-digit number. Now the first digit at the left, it actually corresponds to the alloy group. So this alloy group, for example, if it's 1, then you refer to the table. If the first number is 1, then it means that it's a carbon steel. If it is 2, then it is a nickel steel. If it is 3, then it's a nickel chromium steel, so on and so forth. Okay, so you have to refer to the table in order to interpret this. But the number 1, that refers to the carbon steels. Now the second number, it corresponds to the specific alloy group. So for example, if it's 0, then it just means that it is just a plain carbon steel without alloying elements. If it is 1, then it means it is resulfurized, or if it's 2, that's resulfurized and rephosphorized, or 5, it has a non-resulfurized and a manganese content of greater than 1.0. Okay, now the last two digits right here, we have a carbon content in 1/100%. Now take note, that's the 1, right? In this is the number divided by 100%. Okay, so for example, we have a AISI 1020. Okay, so the meaning of this material is that we have a carbon steel, because this is 1, and for the 0, it just says that it is plain carbon steel. And the last two digits right here, that's 20 divided by 100. Therefore, our carbon content is 0.2%. Alright, so again, AASI 1020, that's a plain carbon steel with 0.2% of a carbon. Okay, so recall that our carbon content race is just something like 0.15, 0.15 to 1.7% based on our reference. So we are in this range. Okay, another example, AISI 4140. That's 4. So it means that that's a chromium molybdenum. And 1, we have a 1% molybdenum. And for the 40, we have 40 divided by 100, that's 0.4% of carbon content. So a chromium molybdenum alloy steel containing 0.4% carbon and about 1% of the major alloy molybdenum. Okay, now another designation is the ASTM. That's the American Specifications for Testing and Materials. Now, this is another standards or another organizations that sets forth the standards. And it says here that it produced in steel mills as standard shapes and are used in construction industry. Okay, so this is how I remember this. If you see a designation using ASTM, then I usually relate it to the construction industry. But if I see a designation in terms of AISI, then that's I relate it to the let's say automotive or machinery industry. Okay, so here the designation consists of in its simplified form, right? So take note, this is just in its simplified form. The letter A, which stands for ferrous materials, followed by an arbitrary numbers, generally 2 or 3. So for example, we have a steel that's specified or designated as A36. Then we know that this is this is based on ASTM designation. For example, we have A325M. If there's an M, then that denotes metric. Now for the A36, this is actually typical designation for steel bars. And this one, this A325M, that's the typical designation for bolts. I guess I have to change my marker color. Right. So we have bolts right here. And here we have steel bars and also plates and some maybe some I-beams. Okay, so A36 is material for structural steel plates and some shapes. Yield strength is 36 psi. So it just happens that for an A36 designated steel, the yield strength is 36 psi. Now for A325, the standard material for bolts, at least 105 psi ultimate strength. Take note, this is ultimate while the other one is yield strength, and A992 standard material for common I-beams. So the point here is that since you have different numbers, then that corresponds to different strengths and of course properties. Okay, so right here we have a graph taken from the textbook by Richards. Actually, the textbook is Build with Steel by Richards, 2011. We have here, for example, an A36. So this is the stress strain diagram, and we have a steel that's A992, that's for I-beams, and then for bolts we have A325. So of course this means that if you have longer lengths, right here, if you have longer lengths, just means you are more ductile, but less less in strength compared to this one, A3 to 5. That's supposed you have higher strength but less ductile. This is high strength, less ductile. And this one is more ductile but weaker. Alright, now let's go on to tool and die steels. Now, as the name implies, these steels were designed for cutting tools, punches, dies, molds, machinery parts, and similar use. Tool steels are mostly high carbon or high alloy in carbon steel. However, a few types do have low carbon or alloy to give their special properties. Right, so they have actually more strong than the carbon steel. But of course, if you have a stronger material, then in terms of this carbon alloy, then of course you have a less ductile material, which is of course that's what we need in these applications. So you don't want a tool or a device that deforms easily. Okay, so you want a rigid or a much stronger steel for this application. Right, now let's go on to the next material, which is the stainless steel. Stainless steels are characterized primarily by their corrosion resistance. This is the main characteristics of stainless steel. That's the corrosion resistance. Simply because of high chromium content. Right? So we have a chromium content right here. I think that's around 18% or something. That depends upon the types of stainless steel. So high strength and ductility, and plus you have a resistance for corrosion. Now they are called stainless because in the presence of oxygen or air, they develop a thin, hard adherent film of chromium oxide that protects the metal from corrosion. Okay, so the problem is if this layer, hard adherent film, if this layer is scratched or somehow gets destroyed, then that's when that's when it will start to corrode. Now right here in this lower left figure, we have the different surface finishes of a stainless steel. So we can have something like a mirror-like finishes, or we can have something like a hairline, or maybe something like this, the number 1. Now they are also available in plates or in bars, and many more. Okay, for the type and a designation of stainless steel, we have the AISI designation. Now for the types, you have austenitic, ferritic, martensitic, precipitation hardening stainless steel alloys, duplex alloys. Now let's focus here in this austenitic. In terms of series, because the designation based on AISI, it's based on series. We have 200 and 300 series. Okay, so that's why sometimes you would encounter that when they specify stainless steel, they say, for example, SS304, right? So that's stainless steel 304. So it has a corresponding properties, and sometimes it has also what's common also is the 202, 200 series, and probably 316. Now that's 200 and 300 series. The characteristics are moderate strength, non-magnetic, excellent corrosion resistance, and the typical application is is general purpose. For 400 series, we have a chromium content up to 27%. Right, and its magnetic and good corrosion resistance lower ductility. And the typical applications, non-structural applications. Okay, and for the 400 and 500 series, do not contain nickel. Chromium content may be as much as 18%. Magnetic, high strength, and fatigue resistance, moderate corrosion resistance. So typical applications are instrument, valve, springs, cutlery. Okay, these are the I think kitchen stuffs right here. Now let's talk about cast iron. Generally, cast irons are a class of ferrous alloys with carbon contents above 2.14% by weight. Okay, so this is what I was talking about, that in this carbon content arrow line, we have the 0.15, and we have here the 1.7, right, percent. Now, anything beyond this 1.7 is referred to as cast iron. And here, based on another reference, it says that the limiting value is 2.14%. Okay. The application may be found in large gears, brackets, linkage parts, pipe fittings, and many others. Here in the figure shown, we have a, I think that's a flywheel or a pulley. And this one is a gear. This one is a sheave, okay, that's made from cast iron. So again, recall that cast iron, since they have more carbon content, then that means they are more brittle, but more strong. Okay, now let's talk about the aluminum and its alloys. Aluminum, they are characterized by their low strength to weight ratio. Right? Low strength to weight ratio, good corrosion resistance, good thermal and electrical, and relatively, I think, good thermal and electrical conductivity. That's right here, conductivity. And relatively ease of forming and machining. They are available in sheets, plates, foils, rods, and bars in various cross sections, and many more. Okay, so example here, we have let's say a square bore or a hexagonal bar or a round bore or tubes, and even other shapes, as well as plates, and even with different finishes. So this one is referred to as checkered plates. It's also available in stainless steel material and in carbon steel materials. By the way, if there's a plate that has a lot of perforations, for example, we have a plate right here, but it has a lot of holes. Right, so this plate is referred to as perforated sheets. Perforated sheets. Okay, for the Aluminum Association, we have a designation for wrought aluminum, but the designation is based on the Aluminum Association. So this is AA. So this is based on aluminum classification. And this classification system uses 4-digit system plus tempered designations. So example right here, we have, for example, 1, then the XXX. So the first one here, that refers to the alloy type according to major alloying element, which is similar to the carbon steel, right? I mean, the designation is similar to the carbon steels, because the first one refers to type according to major alloying elements. So here, the first one refers to pure aluminum. The second one, it contains copper, and for the third one, it's manganese, and so on and so forth. Now, the second digit is the modification to one of the alloying element, and the last two digit, minimum amount of aluminum alloy. These are arbitrary. Okay, so take note, these are arbitrary except for the 1000 series. Okay, so we refer to it as 1000 series, or for example, if it's 2, then that's 2000 series. Okay. For example, we have a 1000 series aluminum 1050. That means it is a commercially pure aluminum having 99.5% aluminum. Okay, now let's move on to copper and its alloys. Now, copper, it says here that pure copper is rarely used for machine parts because of its relatively low strength compared with its alloys. Now, when you say alloys, we were talking about alloys, but we didn't define this yet. Okay, so alloys basically composed of two or more metals. Okay, now for example, steel is an alloy because it is composed of iron and a carbon. Metals or probably elements. Oops. Okay, so we have here the brass and bronze. When I say brass, it is a copper alloy with zinc as its principal alloying element. When we say bronze, that's a copper alloy with tin. Okay, so with tin as its principal alloying element. Here, for the brass, that's zinc. Now, brass typical applications is cymbals in drums. That's brass. So we have here in this figure, we have a copper. That's how it looks like. So it's more reddish brown. And if you include zinc, then that becomes a brass, and it looks something like this. And if you have tin, then that becomes bronze. Okay, so for copper, it's superior for further processing such as forming, machining, joining, and finishing. Now let's move on to nickel and its alloys. The principal use of nickel is as an alloying agent with steel, to which it imparts corrosion resistance and strength. Nickel alloys are available in the form of plates, so plates, bars, sheets, and many more, except that it says here it is an alloying agent, right? For
sa bahay lang yung ginagawa.
Now, here is the list of some nickel alloys. So if we have a nickel copper alloy, it is called a monal. If it is a nickel chromium alloy, it is called an inconal. If it is a nickel molybdenum chromium alloy, it is called hastelloy, which has a good corrosion resistance and high strength at elevated temperatures. If we have a nickel chromium iron alloy, it's called a nichrome. It has high electrical and oxidation resistance used for electrical heating elements. Right, so this one, for example, the nichrome wire. So it's used, it's a wire, it's actually a wire that when you pass electricity to that wire, it actually heats up. Right. So this is our wire. Okay, now let's move on to another class. So we were done with the metals, although we haven't discussed all of it, but I think that's enough for this given time. Now for the ceramics and glasses, there are another class of engineering materials that are the main characteristics of this class of material is that they are brittle. So when I say brittle, they break without or they fracture without undergoing deformation. Glass or plastic deformation. Now, typical applications are found in building constructions. For example, concrete and glasses, glass windows. But some types of ceramics and advanced ceramics materials are used in certain machinery parts. For example, we have here the brake pads. It's the brake pads. So it's actually made of, or they are a class of ceramic materials. And right here we have a ceramic bearing, ceramic ball bearing. So, and that is under the ceramic material. Now we have here, for example, clay. Examples are clay pots and bricks. And for silica, that's the basis for glass products. And alumina and silicon carbide, so two abrasive materials used in grinding. And examples are grinding block, flattening stones, the ones you use to, so the ones you use to sharpen your knife. That's alumina and silicon carbide. Carbides used for cutting tool materials, nitrides, and advanced ceramics or engineered ceramics. An example of this advanced ceramics is this bearing. Alright, now we'll go on to the polymers and elastomers materials. They are another class of materials that has a wide range of properties. Right, wide range of properties. They are actually commonly referred to as plastics. Now, the main advantage, I guess, is that they are easy to shape and probably you can say low cost. Right? Because, for example, we have here a backpack sprayer. I think the previous designs of this backpack sprayers that is made up of stainless steel. Now imagine if you convert that material into plastics, then of course there will be a reduction in weight, plus the manufacturing method or fabrication method for plastics. They're actually roughly it can be said as it is cheaper as compared to the welding and seaming and things like that. Okay, so intuitively we can say that plastics, they're actually they have or they can produce the lowest cost simply because of the material itself plus the manufacturing process that it undergoes. It is cheaper. Okay, and it's more versatile. Now another one right here we have, I think this is a hopper bin. Okay, so if it's made up of steel, then you have to make a roll, or you have to roll this one, and then you have to probably do some bending right here, or flanging, things like that, or welding. So that depends. But anyway, if you use plastic, then you can just have a one part, something like a monoblock material. Okay, so plus you have also resistance to corrosion. And another one here, we have a something like a rubber cover for mechanical parts. Okay, now it says here, polymers can be classified in many ways. So we can classify polymers in terms of its chemistry. You can also classify polymers. Right? You can also classify polymers in terms of its structures and behavior. But in terms of behavior and why they behave when heated up, they can be divided into three. So in terms of behavior, we have these three classifications. First one is thermoplastic polymers. Basically just means that they are heated, formed, and then cooled in their final shape, and can also be reheated because no chemical bonding occurs. Okay, so you can reheat the thermoplastic polymers. But for thermosets, they set in their physical and chemical properties after an initial heat treatment, and therefore they are no longer affected by additional heat exposure. So they are more stable compared to this, stable in terms of temperature. And of course, that depends upon the applications. So we can just say that these thermosets, they're like the rigid version of plastics. Once they are formed, then they are set already. Now, like for this one, for the thermoplastic polymers, you can reheat it. Now, examples of thermoplastics, we have nylon, we have ABS, polycarbonate, PVC, the polyvinyl chloride, polyamide, and many others. Now here, for the thermosets, we have phenolics and polyesters. Now the last classification, sub-classification of polymers based on behavior is the elastomers. These are polymers that exhibit significant, right here, significant elastic behavior. Okay, so such as rubber, neoprene, silicone, and polyurethane. Now when we say elastic, so recall in our subject in strength of materials, elastic just simply means that it goes back to its original shape. When the load is taken out. Okay, that's the meaning of elastic. So you apply the load, it deforms, but when you unload that body, then it goes back to its original shape. So that's actually the characteristic of rubbers. Now here we have some examples. For example, acetal, acrylic, nylons. They actually occur in many forms. Alright, now let's go to composites. Composites, they are another class of material consisting of, take note, let's say composites, that's two or more phases that are processed separately and then bonded together to achieve properties superior to those of its constituents. So it's basically a combination of two or more phases that when you combine those two classes of materials, it provides a superior property. For example, we have here, this is an example of, I think it's a combination of polymers and wood. Okay, and wood. So because of that, they actually provide a better property than just wood. Now wood actually deteriorates in the presence of moisture. Whereas if you combine the properties of polymers and woods, then you can withstand the deterioration from moisture. Okay, another one is the carbon fiber. Now, this material is actually known for its high strength to weight ratio as well. We have high strength to weight ratio. Okay, so we have this what do you call this? I guess it's called a chassis. Okay, so it's a car chassis, or the framing of a car. Conventionally, it is made up of let's say steel or maybe aluminum or something. Or let's just say steel. Now imagine that if you use steel right here, you have a lot of forming plus the connection between parts or between portions. Then you have to do weldings, rivets or boltings and things like that. But here, if you use a carbon fiber, then you can have a something like a monoblock. You can have a single solid body. Okay, so what you need here is just the form or the mold. Then once it is cured, then it can be shaped like this. By the way, wood is known as a natural composite. By the way, another thing about this composite is, for example, in the application where you want let's say elevated temperature, right? You have elevated temperature. Now, if you want a material that can withstand the high temperature, then I think the candidate would be ceramics, right? So if you want this, the candidate would be ceramics. However, ceramics is actually brittle. So if you want an application where you want to withstand the elevated temperature, but you want a ductile material, then probably you can mix, or some companies actually mix ceramics and metals. Ceramics, right here, I guess we'll write it here. Ceramics plus metals, and that's what they call. I don't know if that's cermet. A cermet. All right. Now I guess that's the end of this presentation, and we will now go to the review questions.
Okay, so yung after po natin ng lecture discussions, then meron po bang questions?
Sir, I think meron po tayo sa chat.
Sige. Okay, so one question is, what does high strength to weight ratio means? High strength to weight ratio. Okay, so yung meaning po nun is, in terms sa per unit weight, mas mataas yung strength na mabigay niya. Okay po ba? So, wala na pong questions. So, yung next po natin is yung review question. So, let's open po yung review questions natin, and then ipi-play ko na lang po yung recorded questions or recorded questions and answer portions po.
Okay, now number 1. The most commonly used metals and have a wide
Sir, excuse me po.
Yes po, ma'am.
Sir, can they ask questions po during the recording or after the recording na, sir?
Ma'am, ano na lang po, after.
After. So, ipunin na lang muna nila yung mga questions nila dun sa mga problems. Okay, sir. Thank you.
I-play ko na po yung yung next.
Yes, sir.
Okay, now number 1. The most commonly used metals and have a wide variety of applications. Answer is letter A, carbon steels. Number 2. The meaning of AISI. The answer is letter C, American Iron and Steel Institute. Number 3. The meaning of SAE. Letter C, Society of Automotive Engineers. Number 4. If the plate used in an agricultural machine is designated as AISI 1040, what is the carbon content? It's right here. We have, right, sorry. So we have AISI 1040. Now we have this number right here, and that number, that a 2-digit number corresponds to the carbon content. That's 40 divided by 100. That's equal to 0.4%. Okay, so the answer is letter C. Okay, number 5. Number 5, a type of carbon steel less than 0.3% carbon, also called mild steel. Okay, so this is letter A, low carbon steel. Number 6, a type of carbon steel that's carbon steel having 0.3% to 0. I think this should be a type of carbon steel at least having 0.3% to 0.6 carbon. The answer is medium carbon steel, letter B. Okay, so let's write it here. We have low carbon steel, and here we have a range of less than 0.3%. Now for our medium carbon steel, we have 0.3 to 0.6%. Okay, number 7, a type of carbon steel having greater than 60% carbon. So that's high carbon steel. So 0.6. Okay, so take note, I think this should be 0.6%, not 60%. Okay, so this must be 0.6%. So this is high carbon steel. All right, number 8. The higher the carbon content of the steel, the blank it becomes. This is 5, this is 6, this is 7, and number 8, we have. Right, so for number 8, recall that we have this carbon line, and we say that the increasing the carbon means increasing the strength, and increasing the carbon decreases the ductility. So the answer of number 8 is letter C, stronger and more brittle. Number 9, for agricultural machines, the material used for standard shaft is of steel designation with designation 1020, cold rolled. What is the type of steel used? So we have here 1020 or AISI 1020. So we have the number 1, that simply means plain carbon steel. Plain carbon steel. Okay, so the answer is letter C. Number 10, what is the percentage of the carbon? So it's just, so since we have 1020, then it just means we have 20 divided by 100, so that's equal to 0.2%. Number 11, what is the recommended material for the manufacture of pin sleeves and hitch pins for walking type power tillers? This is cold rolled steel. Okay, so number 11, that's letter B. Okay, we will be able to describe this or explain this after our next topic on manufacturing processes. Okay, basically when you say cold rolled steel, it's an additional process at room temperature wherein you are actually pressing the materials by 2 rolls. For example, we have these rolls right here, and this is our material or plate. All right, so it is being pressed. So in that way, because of cold rolling or because of pressing, then somehow there's a change in the microstructure of the material. Somehow it gets stronger as compared to hot rolled. Okay, so the answer is letter B. Now number 12. For the number 12, it is a material commonly used as axle for agricultural machines. That's cold rolled steel shaft. Number 13, it is a type of steel used for making tractor drawn disc plow bottoms. We have We have tool steel, we have soft center steel, molybdenum steel, and none of the above. The answer is, for number 13, the answer is letter B. That's soft centered steel. Okay, so somehow it's actually a manufacturing, it's under the a manufacturing process that the center is softer as compared to the outside surfaces. Okay, number 14, steel bars commonly used in the manufacture of agricultural machines. Number 14, the answer is B. That's mild steel. Number 15, it is a type of steel used in turning machines for cutting metals. The answer is letter C, tool steel. Number 16, it is a type of steel commonly used as a peg tooth for axial flow rice thresher. The answer is that's letter D, which is cold rolled steel. Okay, so why do we need this cold rolled steel? Or we can have an acronym of CRS. That's CRS, cold rolled steel. Okay, because we need a weldable, although we need a strong material, but we also need we need that it can. We need the weldability property as well. Okay, as compared to tool steel, that would be difficult to weld. Okay, number 17. In number 17, the required material designation for the construction of gear based on PAS standards. So this is based on PAS. That's letter B. It says AISI 1045. Okay, number 18, the type of steel used in the manufacture of disc plows and displays for harrows. The answer is letter C. That's AISI 1080. Okay, so that's this can be found in our past volumes. Okay, number 19, these are steels characterized primarily by their corrosion resistance due to high chromium content, and that's stainless steel. Okay, number 20. Stainless steel is basically an iron, is basically an alloy of. So number 20. Basically, stainless steel is an alloy of iron plus chromium. And the answer is letter A. Number 21. For the number 21, if the stainless steel used in a banana chipper is designated as 316, the designation is under. So this is the most, let's say, or the common designation for stainless steels is based on AISI. So that's 300 series, and the answer is letter B. Okay, number 22, it is the series of stainless steel that are non-magnetic and have excellent corrosion resistance but are susceptible to stress corrosion cracking. The answer is letter A, austenitic. Number 23, it is the series of stainless steel having high chromium content. Okay, having high chromium content up to 27%. The answer is letter B. That's the 400 series. Ferritic. Number 24. These are type of stainless steels typically used for cutlery, surgical tools, instruments, valves, and springs. The answer is 400 series, 24. But although 400 series, that should be martensitic. C. Martensitic. Right, and that's 400 or 500 series. Okay, number 25. Number 25, these are type of materials designed for high strength, impact toughness, and wear resistance at room and elevated temperature, commonly used in forming and machining of metals. The answer is letter D. That's tool and die steel. In number 26, which of the following metals is the strongest? We have tool steel, spring steel, stainless steel, all of the above. So the hardest is tool steel, letter A. Okay, number 27. So for number 27, it is a type of steel used as a shock absorber attached to the wheel and to the thresher support frame in mobilized thresher. This shock absorber, it looks like this. For example, this is our wheel. Right? This is our, let's say this is our axle. So somewhere right here, there is something like something like this. So there's actually a spring. It's called a leaf spring, right? So there are layers of leaf spring over here. If we try to look at the side view, this is our wheel. Then we have something like this, right? So we have leaf spring right here, and this is, I mean, the material used in here is called spring steel. Okay, number 28. So for number 28, it's a class of ferrous alloys with carbon contents above 2.14%. The answer is cast iron, letter C. Number 29. It is a material characterized by their high strength-to-weight ratio, high thermal and electrical conductivity, good corrosion resistance, and good manufacturing properties. Okay, so the hint right here is the high strength-to-weight ratio, and that is attributed to aluminum. Number 30. Which of the following wrought aluminum series corresponds to commercially pure aluminum? So recall our designation for aluminum, and the T1000 series, that corresponds to the commercially pure aluminum, 1000 series. Okay, number 31. For number 31, it's a material having the highest strength-to-weight ratio of all metals. Okay. Good strength and corrosion resistance at high temperatures. So we have a high strength to weight ratio, but it is corrosion resistance at high temperatures. This would be titanium. Okay, number 32. For number 32, it is a material characterized primarily by their high strength at elevated temperatures, composed of molybdenum, niobium, tungsten, and tantalum. So these are refractory metals. Refractory metals. Okay, so from the word refractory, that I think it can be related to the elevated temperature. Okay, number 33. It is an alloy of copper and tin. Okay, an alloy of copper and tin. That's bronze. right? Number 34, it is an alloy of copper and zinc. The answer is brass. Okay, number 35. It is an alloy of nickel, molybdenum, and chromium. So this is a nickel alloy. The answer is letter C, hastelloy. Number 36. For number 36, it is an alloy of tin, copper, and antimony. The answer is letter D. Okay, pewter. Okay, next is number 37. Well, for number 37, they are substances that melt on heating and are processed in the state by a variety of extrusion and molding process. Okay, that melt on heating. So this is thermoplastics. Number 38. They are substances that cannot be melted and remelted. If you recall our discussion, that's thermosets. So it has a stable characteristic in higher temperature than the thermoplastics. Number 39, it is the temperature at which the plastic can withstand without incurring a change in its physical properties. And the answer is service temperature. Okay, now I think you should refer to PAS regarding this engineering of plastics. I'm not sure about the PAS number right here, but anyway, you can just find it in volume number 3. Okay, number 40. Number 40, which of the following is not considered as an engineering plastic? The answer is letter E, none of the above, because they are all plastics. 41, polyamide is one of the most versatile and widely used thermoplastic materials. It is also known as, okay, it is known as nylon. And number 42, which of the following does not belong to the group? Wood, ceramic, carbon fiber, fiber reinforced plastics. They are all composites. So the answer is letter E. Now again, you can find the definition about this nylon and other polymer stuffs in PAS volume 3. Just not sure about the PAS numbers. Anyways, that's all for these review questions. Now we'll move on to our next topic, which is the manufacturing processes.
So, meron po bang questions so far? Sige po. If no questions po, then I'll play yung next natin na topic, which is manufacturing processes.
Do you have questions? None? Nakatulog na ata. None po. Okay. How about you, Jerome? Tahimik ka ata. Oh, nakamute. You can raise hand kung gusto nyong kung gusto niyo magsalita. Okay, sir. Parang wala naman pong questions. Let's proceed na po with the next topic.
this is our second topic for the review course in machine design. The title of this topic is manufacturing processes. For the contents of this presentation, we'll first discuss what is manufacturing, and then we'll have a classification or something like an organizational chart regarding the manufacturing process. And then after that, we'll have a detailed discussions regarding the different processes such as the metal castings, hot rolling, and cold rolling. So if you remember earlier, we mentioned about cold rolled steel. So in here, we'll have a detailed discussions about that. Okay, and machining of metals and many more, since there are a lot of processes. Okay, what is manufacturing? Now, according to Groover 2015, it says that manufacturing can be defined technologically says we have a technological description about manufacturing, and it says that it's the application of the physical and chemical process to alter the geometry. Okay, so it's about altering the geometry, the properties, and or appearance of a given starting material to make parts or products. For example, we have a solid shaft right here, and we want to make a step shaft. So how do you make a step shaft out of this plain solid shaft? And of course, you have to undergo the milling operations. Okay, so the alteration of geometry, and for some process, it also alters the properties, and that's what that's the definition of manufacturing. Now, another definition of manufacturing is in terms of economical definition. So in terms of economics, manufacturing is the transformation of materials into items of greater value by means of one or more processing and or assembly operations. So of course, from this state or from this condition, and of course you did some processing operations to improve the value. Okay, so in the end, you have a greater value product. Now, for the classification of manufacturing process, so for example, here we have the main manufacturing process. It is classified into processing operation or assembly operation. Now, for the processing operations, we can have shaping process. So, any process that's about formations or shapings, rolling, things like that. Then that's under this shaping process, which can be further classified as solidification process, like the casting. And we have also the material removal, because it actually, in this removal of material, for example, drilling or milling, you are actually changing the shape. Okay, and also this one, the deformation process, and still many others. Okay, another one, another example of processing operation is the heat treatment. So here you are actually changing the properties, not just the, not just the geometry, but rather the properties itself. Okay, and we also have surface processing. And for assembly operations, we have welding, brazing. Okay, so welding basically is just fusing the two parts. You're fusing two different parts into one. So we can have it by welding, or we can have it by brazing and soldering. So this is less temperature than welding, and of course different applications and different metals. And we can also have, or we can join parts as well using mechanical fasteners such as bolts and other mechanical fasteners. And lastly, we can have adhesive bonding, so the use of chemical liquids and stuff like that. Then that's also about joining, okay, joining the parts. Okay, now let's talk about metal casting. So casting is a type of solidification process in which liquefied material such as a molten metal is poured into the cavity of a specially designed mold and allowed to harden. Okay, so here in our figure we have a molten metal and it's being poured into a mold. So in that way, the main advantage is that you can create a complex and intricate shapes, both solids and hollows. So since the phase of the molten metal is in liquid, then of course it will just follow the shape of the mold. Okay, so in that way you can create a complex and intricate shapes. Now, hot rolling and cold rolling. We have already discussed this. You have already encountered this in the previous lecture. That's cold rolling. Rolling is a deformation process in which the thickness of the work is reduced by compressive forces exerted by two opposing rolls. So rolling, that simply means we have two rolls. Alright, so roll number 1 and then roll number 2, and then your material is in between. But when we say hot rolling, it just simply means rolling at elevated temperature. So, for example, in this case, the lower left, and when we say cold rolling, refers to rolling at room temperature. So we have here the lower right. So it doesn't mean that when we say cold rolling, it has to be at some freezing temperature. Anything or any temperature that's just somewhere in this room temperature interval, then that's classified as cold rolling. And there's an effect between there's an effect in the microstructure of the metal when you undergo hot rolling or cold rolling. And by the way, you would notice that our classification here, we have this classification, but our detailed discussions, they're not actually named according to these classifications, simply because it's much more common to encounter this term, like for example metal casting, okay, rather than deformation process or solidification process. So this is more common term, and that's why I decided to discuss the detailed discussions regarding using this common term. Okay, so hot rolling. Now for cold rolling, we can actually see the difference between cold rolling and hot rolling. So here in our upper left figure, we have the microstructure or the gray structure of the metal or the steel, and we can see that there's actually a difference in terms of the microstructure. And in terms of the surface, we have here, taken from Metals Depot, we have hot rolled sheet and cold rolled sheet. So you can actually see the difference. But in terms of properties, we say cold rolled steel is actually more, they have a smoother appearance as compared to the, or smoother surface as compared to the hot rolled sheet. Plus, it is much more stronger. Much more stronger as compared to the hot rolled sheets. All right, now let's move on to forging of metals. Now, when I say forging, it just simply means that it's a forming process and shaping process for metals through the use of hammering, pressing, or rolling. So typically forged products are bolts and rivets connecting rod shafts of turbines gears. So we have here in the historic times we see this type of process in the movies. Okay. Now let's move on to the extrusion and drawing of metals. The question here is how would you make a product of this shape or cross-section? And that's actually by extrusion process. Here, extrusion is the process of forcing a billet through a die to reduce its cross-section or to produce a wide range of solid or hollow cross-sections. So generally carried out at elevated temperatures simply because it's more fluid in elevated temperatures than in lower temperatures. So here, this is our billet. So it's like our raw material or raw product, and this is our die. So it is being forced out. So that depends upon the shape of the die right here. So depending on the shape, then you can produce a wide variety of cross sections. Okay, next topic: machining of metals. Milling operation is a material removal process in which excess material is removed to achieve the desired geometry. So here we have, I think, grooving of shafts or making some parts that's complex. So you can do it by machining, and it's actually precise. Machining process is a precise process. The three most common types of machining process, we have turning, milling, and drilling. Now the difference between the three is that when you say turning, you have, or let me explain this first. When you say machining, you must think about a cutting tool. There must be a cutting tool, right? Number one, there must be a cutting tool, and number two, there must be a workpiece, right? This is our workpiece. So when you say turning, the workpiece rotates while the cutting tool is stationary. So in this case right here, so in this case we have this is our workpiece, and it's being held by this jaw, something like a holder, and this is our cutting tool. So this one rotates, this workpiece, all right, workpiece rotates, and this is our cutting tool. Okay, and for milling, the opposite is what is going on. So for the milling, the workpiece is stationary, but the cutting tool rotates. So this is our workpiece, and I think it is stationary with respect to this cutting tool, and this is our that's tool, cutting tool. Okay, so this one rotates. So as it rotates, because it has some specially formed blades right here, so it somehow chip off the materials and thereby removing some materials. Okay, so this one rotates and this one is stationary. And when you say drilling, it is used to create round hole. So something like a mill, I think it is related to milling as well, except that the function is to create round hole. Okay, another one, grinding. Grinding is a material removal process accomplished by abrasive particles that are contained in a bonded grinding wheel rotating at very high surface speeds. So for example, we have a bench grinder. It's used to remove some, let's say, surface, what do you call that? Surface roughness. So for example, you want to smoothen the surface or something, then that's the grinding process. And here in our lower right figure, we have a power grinder. Okay. Now the next one is sheet metal forming. Sheet metal working includes cutting and forming operations performed on relatively thin sheets of metal from thickness 0.4 mm to 6 mm. So when we say sheet, that's actually 0.4 mm to 6 mm. Although another common designation for sheets is in terms of gauge, which just for example, it is referred to as gauge 20 or schedule 20, gauge 20, gauge 18, right? Example GI sheet, gauge 18. So that refers to thickness, right? This refers to thickness. Okay, and if I remember it correctly, I think it's like 1 inch divided by that's 1 inch divided by 18. So that's the thickness. 1 inch divided by 18. That's your thickness. Okay, and that depends again from which reference did you take these values. So here, from one reference, it says that we have a 0.4 mm to 6 mm. That's around 1/4 inch thick. We can refer to it as a sheet. Anything smaller than 0.4 mm, it's called a foil. Now, this is a foil. This is a sheet. And right here, we have anything larger would be referred to as a plate. Okay, so for example, MS plate 10 mm. So mild steel plate. Let's write it here. MS plate 10 mm. So that's a mild steel or a low carbon steel. I think that's another name or another way to call the low carbon steel is the mild steel. Mild steel plate, and the thickness is 10 mm. Okay, so sub-classification, usually in the text, the sheet metal forming is actually a separate chapter because there's a lot of operations that you can do for sheet metals. So sub-classification is the bending operations. We can have V bending or roll bending or seaming and many more. So bending, so we can have this the bender. So we feed this sheet, and then this one goes downward. This one goes downward, and you notice here we have something like a V groove, like right here. So it bends. It bends the sheet into, I think this is 90 degrees. For roll bending, this is commonly referred to as roller. So we have 3 rolls here, and you feed the plate, and then you rotate the rolls, and somehow you can achieve this circular form. You can also do conical forms here. Okay, another one here, we have cutting operations. So shear cutter or hydraulic shear. So we have here. So you just feed the metal sheet, and then somehow it cuts the sheet by shear. We also have drawing operations and die and press operations. Okay, so I didn't have a picture regarding drawing operation and die and press operations, but I guess we can just say for drawing, probably we can have a section like or a form. Let's say something like a cup. So a steel cup. It's more. This is manufactured using drawing operation. And for die and press, for example, you have some I think car body shapes. You can have that, or anything similar. Okay, now let's move on to processing of polymers. Typical process for polymers, we have extrusion, injection molding, blow molding, and roto molding. For the extrusion process, this is something like the extrusion for metals. So basically, we have this equipment, and this equipment is equipped with heaters. We have heaters here, so they are band heaters. We have the inlet right here. Here's the inlet, and here's the outlet. Okay, so you feed in the plastic pellets in this point, and because of the screw rotation, there's actually a movement or a transport of material from this point to this point. Okay, so you have here a shaping die. So that, again, depends upon the die. You can have various cross sections, like for example, tubes, pipes, sheets and films, structural parts. So something like this. Except that this is for polymers. Here we have the next process is the injection molding. Basically, it's almost the same as the extrusion process, except that instead of having a die, right? Instead of having a die, you have a mold. Okay, so that's injection molding. So it's more on, I think it's more on solid forms. It's instead of having a die or an orifice, you have a mold. The next one is blow molding. For the blow molding, it's something like the injection molding, except that you are introducing an air right here. You are blowing air inside, and that's the reason why this bottle container is being shaped like that. Okay, so that's by blow molding process. Okay, so you feed. Well, first you feed the plastic pellets or the plastic outputs, and then after feeding, then you introduce the air, and because of that air, then that actually presses the plastic into the surface. And if you remove the mold, then you can have this final shape. The next one is rotomolding. Now, rotomolding, think about rotation. So we have this container right here. Let's say cylindrical container or tapered or something like that. The first step is to fill this container with pellets. That's charging. Okay, so after filling this container with pellets, then you have to enclose it. Right? You have to enclose it, and you have to heat the device. So because of elevated temperatures, then of course these plastic pellets will melt, and you combine that with rotation. So this one rotates as well. So I guess you have a 2-axis rotation. So in that way, because of the rotation, the plastic will have, or the plastic will stick into the surface because of centrifugal force. Okay, so once done, you have to reduce the temperature. It's being cooled down, and then afterwards, if you remove the mold, then you can have this shape. Okay, so these are common in large, large containers. I think you can have large containers. Okay, next one is heat treatment. Now, heat treatment is a process in which a metal is heated to an elevated temperature from which it is cooled very rapidly. So we have heating, and we are going to cool it very rapidly. And in the process, the metal somehow gets harder and stronger. Okay, so right here, we have the figure of heating of metal. And right here, we have a picture for quenching of heat metal. So that's cooling the heated metal very rapidly. Okay, that's the term quenching. Okay, but the way to understand this heat treatment is that we have to look at the grain structures of the metal. So here we have a ferrite grain and we have a pearlite grain. Now the point here is that we have, we'll have a different forms or grain structures depending upon this. Let's say here we have ferrite, we have pearlite and cementite. Okay, another one right here, we have austenite. So this is the grain structures, and we have if we cool it very slow, then we have, or we are actually changing it into this structure. If we are going to change it very rapidly, then we are changing it into this structure. So the point here is that once you heat up the metal and then you cool it down, then you are actually changing the microstructure of the metal. So that depends upon the rate of the cooling, then that would also corresponds to the properties, to the final properties. Now right here at the back we have an iron carbon alloy phase diagram. So here we have the carbon content present by weight. At the x-axis we have the carbon content present by weight, and here we have the temperature. Now you would notice that right here we also have temperature, but in terms of degrees Celsius. So if you see here 210 degrees Celsius, that's actually beyond the boiling point of water at atmospheric pressure. So somewhere, let's say we have a steel that has a 0.5%, for example, and it is in room temperature. Now the point of this, when we heat up the metal, we are actually increasing we are elevating the temperature. Okay, so right here. So let's say we heated it up into this point. So from this phase, pearlite and ferrite, we are changing it into austenite. And I know you have already heard this austenitic ferritic steels or stainless steels. It all relates to this phase diagram. Okay. Okay, so again, we are from this normal temperature or ambient temperature. We are heating up the metal and increasing it to this temperature. Now at this temperature, the structure of the metal is already different from this one. So you are bringing it here to this point, but if you cool it down rapidly, then if you cool this down very rapidly, then you are bringing back the temperature, but you are retaining the properties. Okay, retaining the properties. Okay, so you heat up and then you are changing the properties, and then you cool it very rapidly, and then you can retain the properties of this austenitic region. Okay, so now let's move on to the surface processes. The surface operations includes honing, lapping, super finishing, polishing, and buffing. The figure right here, as shown, is the knurling process. So you are making some grid lines in here, okay, just for grips, for example. Okay, now let's move on to the joining process. Now the joints can be classified as either permanent or I think this should be non-permanent. So permanent or non-permanent. When I say a permanent joint, it is that when disassembling, it will cause unrepairable damage to the base metal or to the joint itself. So for example, this is the joint, right? This is our joint. Now if I want to disassemble this, then I have to break this joint, or if I have to break the base metal. This is our base material. If I damage either one of these, then that's called a permanent joint. Now, if during a disassembly I don't damage the base material, or I don't damage the joint, then that means that joint is non-permanent. Okay, so non-permanent joint, example of this, bolting. And this one, permanent joint, this is example is welding and probably bonding, adhesive bonding. Okay, so mechanical fasteners. We are in this non-permanent joint, so there's a lot of mechanical fasteners out there, combinations of bolts and nuts, screws. By the way, what's the difference? Let me ask you a question. What's the difference between, right? What's the difference between a bolt and screw? Right, so that's the $1 million question. What's the difference between bolt and screw? Okay, so if I draw here, say we have something like this, and let's say we'll have a threaded portion all throughout the length, and let's say we'll draw another fastener here, also threaded all the way throughout its length, and let's call this bolt, and let's call this screw. Now, what is the difference? And let's say this is, I refer to hex head. So let's say this is also hex head. Okay, this is also hex head. This one is also hex head, but I call this screw, and this one I call this bolt. Now, what's the difference? Okay, the difference is a bolt is to be mated with a nut. Mated with a nut. Whereas, this one is bolt, and here this is to be mated, or I think the right term is to be inserted into a tap hole. Okay. So when we say tap hole, for example, we have a cross section right here, and I drill a hole, but I drill it with a thread, or I drill it having a thread. So that's what you call a tap hole, or let's call this a hole with threads. Alright, so that's the meaning of the tap hole. Okay, so right here we have this screw. So this is our screw, although even though they have the same heads, let's say hex head bolt or hex head screw, as long as the intention is you are going to mate it with to mate it with a nut, then that's a bolt. But if you are going to insert that into a tap hole, a threaded hole, then that's a screw. Now, because of let's say they can have the same geometry, maybe some screws have the same geometry as the bolt, and therefore sometimes you can it is possible, or probably it exists, that a nut can be fitted into a screw. But again, the main difference is that the screw should be top hole and the bolt should be nuts. And we have here stud and nut. When you say studs, it's basically a threaded, something like a threaded fasteners, entirely threaded fasteners, and this is the nut. So it has no head. And you have this point right here, tip point. But if it's long enough and it's something like a rod, then we can just say that it's a threaded rod, right? This one, threaded rod, and you have actually a knot here, plus you also have a knot right here. Now, when the back part of the machine is inaccessible, the use of bolts would not be appropriate, hence a rivet is rather used. Okay, so a rivet, it is much faster, and probably it can also provide some functions that can be provided by the bolts. Okay, so now let's move on to welding. Welding is a process of fusing materials by melting the edges and often adding molten filler material. When we talk about welding, we have to think about this American Welding Society. That's the governing organizations for welding. American Welding Society, or AWS, they're the ones developing the codes and recommended practices and guides. Right here, we have one type, or the most common type of welding. That's the stick welding, or technically referred to as the shielded metal arc welding. While this one, I guess, I think this is TIG welding. Okay, so for the shielded metal arc welding, or SMAW, it is commonly referred to as stick welding. Why? Because you have this stick right here. This electrode, this stick, this is technically referred to as the electrode. And in operation, the electrode is attached to the electrode holder. You have this holder, right? You have this holder, and you have this clamp, a work clamp, which is attached to the base metal to provide the current flow. And here we have the said electrode, or the AKA welding rod, is a consumable part of the shielded metal arc welding process. So we have different types of of this welding electrode. So for example, here we see that this is 6011, and here we have 6013. This one is 7014. So what is the meaning of all this? Now here we have, for example, it is designated as E6011 or E7018. The E stands for electrode, and the 6, the first digit right here, I think not the first, the first two, right? That refers to the tensile strength in KSI. Tensile strength in KSI. Now, I think this is the tensile strength of the joint. I should say that it's the tensile strength of the joint. Assuming that we have a proper, assuming that we did a proper welding procedure. So that's the joint. Now, for example, we have a base metal, let's say a mild steel plate, or a flat bar. That's right here. Let's say we have a flat bar, and I have to attach another flat bar right here, and therefore I have to weld this portion. Right, so if I have to weld this portion, recall that if this is a mild steel bar or mild steel plate, we have a 36 KSI, A36, right? This is A36. And the joint here, it says we have a 60 KSI. So the joint is always stronger than the base metal. And that's of course the assumption that we did a proper welding. But of course, if we didn't do a good welding job, then that will just rip off. Okay, so this one refers to the tensile strength of the joint. And number 1 right here, the third digit, that's correspond to the welding position. So I guess if I remember it correctly, when you have a number 1 position, that's I guess that's all position. So in other words, you can have a flat, you can have a horizontal, and you can have a vertical, plus you can have also overhead. Okay, so when you say flat position, it's actually I think it's very hard to draw right here. For example, this is our plate, and that's in 3D, and this is our joint. Now let's say this is our XYZ. Right, so the welding electrode is positioned right here, so that's a flat position. Now if you have if we talk about the horizontal position, let's say this is the wall. It's welding on the wall, but the direction is horizontal. All right, so if you are welding along this line, okay, so take note, this is the wall, and this is our welding direction. Then this is a horizontal position. And when you talk about the vertical direction, then this is the vertical direction. And when we say overhead, basically you are welding something like, this is the ceiling, this is the wall, this is the floor. Okay, so if you are welding, let's say looking at the ceiling, or the ceiling is above you, then that's what you call overhead. And the number 8 right here corresponds to the type of coating and the current setting for the electrode. Okay, so that's the previous one was the shielded metal arc welding. Now this is the tungsten inert gas, or TIG welding, TIG welding, or tungsten arc welding, which uses a non-combustible tungsten electrode to create an electric arc with a workpiece. The inert gas used for shielding is typically argon. Okay, so you have an argon gas right here, and this is your torch. So you don't use any electrodes right here. You only use a non-consumable tungsten electrode, not the ones with the not the ones used in the shielded metal arc welders. But you still have this work lump. Okay, now another type of welding is the MIG welding, or metal inert gas, or gas metal arc welding, or GMAW, which uses a continuous wire. So take note, use a continuous wire fed into the welding gun instead of an electrode. So this is your welding gun. There's actually a wire here. So this is a wire, a spool of wire. So this wire actually runs through this cable, and then it exits in this welding gun. Okay, and we have a shielding gas. This is the shielding gas, which is usually carbon dioxide, which is used for shielding. So there's also another passageway for the carbon dioxide. Okay, another one, oxyacetylene. burns acetylene gas to generate a torch that can be used for welding. Take note, it can be used for welding, brazing, or even cutting all types of metals by changing out the attachment or tips. These are the tips. Now, another $1 million question. We have a smaller tank, right? And we have a taller tank. We have a taller but thinner or narrower tank. So we have here a fatter tank but smaller in terms of height. So the question is, which one is oxygen and which one is the acetylene, right? So which one is the oxygen? Is it one or is it this? Is it two? Okay, so the answer is the oxygen is the tallest tank, and the smallest tank is the acetylene. Okay, so right here, so this is oxygen, this is acetylene. Okay, so they all have these valves right here, and then they mix us together somehow in this torch. So depending upon the torch, then you can have a welding head, a cutting head, or a heating head. Alright, so this is some close-up view regarding this torch head. Okay, now let's move on to brazing and soldering. So soldering and brazing are closely related processes in which metal components are joined together by means of a filler metal. The filler metal, which has a melting point lower than that of the base metal, is introduced to the heated joint. So right here at the lower left we have brazing, and at the lower right we have the soldering, which is typically in the typical process for electronics industry. Here, which is typical in refrigeration industry. Okay, and it uses a metal, a filler metal. Okay, now the last one we have the adhesive bonding. So many components and products can be joined and assembled by the use of an adhesive rather than by one of the joining methods described thus far. So basically it's just glue. When I say adhesive bonding, you can combine various parts by using glue. So there are several forms. It can have a liquid or a paste or solution or emulsion, powder, tape, and film. So the design of that actually depends upon how did you apply the adhesives. Is the loading in shear or tension or peel or something like that? Okay, so you have to take into considerations those things. Now another one right here, we have this most common probably. It can actually join even rubber, leather, or metals, or various materials. Okay, now we're almost done, and right now we'll move on to the review questions.
Okay, so may questions po ba so far regarding sa lecture discussions? Yung sa shielding it's about pag nag-fuse yung metal doon, parang somehow parang i-cover, merong gas na doon na mag-cover sa joint na yon. Okay, any more na questions po? Yes, actually may mga welding machine na inverter talaga. So in that way parang mas ano eh, kasi 'di ba yung lumang style ng mga welding machine, yung mga malalaki. Nag-off ba? Kaya yung old style ng mga or old design ng mga welding machine, yung mga malalaki, dapat kailangan mo siya i-tap dun sa parang sa main entrance pa eh. Pero kapag gumamit ka ng mga welding machine, mga inverter type na welding machine, so pwede mo na siya masaksak sa mga convenience outlet lang. Okay, yung question is there any significant difference? I think meron siguro kasi in terms sa kung makita mo din sa may welding machine mismo at saka sa mga electrode, may nakalagay doon na pag yung amperes mo doon ay pang AC or pang DC. Plus yung ano niyan, syempre kapag inverter type, hindi mas less yung ano doon, yung sa I think yung sa consumption yata kasi kino-convert niya yung AC, i-convert niya into DC. With respect naman sa welding job mismo, hindi ko pa na-notice yung difference doon. Kasi yung ano ko pa lang, yung na-try is yung sa inverter type. Pero sa mga ibang welders, yung sabi nila kapag yung sa AC na type, parang mas makakaluto daw siya or siguro mas makaka-fuse or mas makaka-weld ng siguro mas mataas yung temperature doon for a given same na ampere setting. So yun yung mga ano nila, yung mga comment. Okay, so ako na magtatanong yung next yung question and answer portions natin for the topic number 2. So please ready yung review material natin.
All right, now let's refer to our review questions, and we are in let's use this color, and we are in number 43. So for number 43, it is a manufacturing process in which a sharp cutting tool is used to cut away material to leave the desired part and shape. The answer is letter A, machining. Okay, number 44. It is a material removal process that uses an individual abrasive grain as the cutting tool. We have letter B, that's grinding. The key word right here is the abrasive grain. Number 45. It is a deformation process in which the thickness of the work is reduced by compressive forces exerted by two opposing rolls. The answer is letter C, right, rolling. Number 46. It is a deformation process in which the work is compressed between two dies using either impact or gradual pressure to form the part. Okay, so the keyword right here, we have a deformation process, and either by impact or gradual pressure to form the part, that's forging, letter D. Number 47. Now, in manufacturing, it is defined as the straining of the metal around a straight axis. The answer is letter C, bending. So for example, we have right here our V bender, and if this is our metal plate and we are to, okay, it's very hard to draw here. We have this top portion that goes downward. So if we try to look at the side view, we have something like this. We have this bottom part and we have this top part, and this is our plate. So of course, when this go down, then of course you will have a bended, right? We have a bended shape, and right here, this is the straining portion. Okay, straining portion. Okay, number 48. Number 48, it is a process in which molten material flows by gravity or other force into a mold where it solidifies in the shape of the mold cavity. The answer is casting. Number 49. It is a general term that refers to the process of heating a material to change its physical properties. This heating and eventual cooling to room temperature either softens or hardens the metals. The answer is A. That's heat treatment. Okay, number 50. It is the first step. Okay, so the first step is letter A. That's austenitizing. So you are bringing this this ferrite structure into an austenitic structure. So it's also termed as austenitizing. And the second step, right? So if we have here, so we first increase the temperature, right? And then the second step probably goes down. So this first step, this is the austenitizing. Let's say this is our temperature, and probably this is our time. So maybe we have a steeper slope right here. This process, this second process is quenching. Okay, so this is quenching. Austenitizing, number 50, and number 51, the answer is letter B. That's quenching. Okay, number 52, which of the following is used as quenching media for heat treatment? The answer is all of the above. Number 52, we have all of the above. Number 53. Okay, number 53, it is a process of reheating the hardened steel to much lower temperature. So if we have austenitizing, and then probably we have this, we have another process like quenching, and then we are to increase again, but at a much lower temperature. Then this one is termed as tempering, letter C. So that's tempering. Number 54, which of the following is considered as softening process for heat treatment? The answer is all of the above, letter D. And number 55, it is a hardening process of heat treatment by diffusing carbon or nitrogen into the surface at an elevated temperature and then cooled at a rate sufficient to harden the surface. So this is letter A, case hardening. So in this way, you are just actually hardening the outer surface. Okay, number 56. So number 56, it is a shaping process for plastics where the material is compressed or forced to flow through a die orifice to provide long continuous product whose cross-sectional shape is determined by the shape of the orifice. Okay, the answer is letter A. Number 57, it is a process in which a polymer is heated to a highly plastic state and forced to flow under a high pressure into a mold cavity where it solidifies. This is letter B, injection molding. This one, the above right here, it uses a die, while this one, injection molding, uses a mold. Okay, number 58. Which of the following processes are used to make a hollow seamless parts out of thermoplastic polymers? The answer is letter C, rotomolding. All right, number 59. Number 59, which of the following is not a permanent joining process? The welding is permanent, brazing is permanent, soldering is permanent. So the answer is letter D. Number 60, which of the following joining processes has the least amount of heat involved? So we only have a process or processes that involves heat or welding, brazing, and soldering, and the least would be soldering. That's letter C. Number what else? Number 61. The largest amount of heat, that's welding. Number 62, it is a joining method whereby the materials being joined are melted at a very high temperature to make a strong, permanent joint. So that actually refers to any type of welding process. So the answer is letter D. Number 63, which of the following welding methods does not use any gas as cooling element? The answer is letter A. Why? Because the MIG welding uses a carbon dioxide. The TIG welding uses argon gas. So the answer is letter A. Number 64, which of the following welding methods uses carbon dioxide as dioxide gas as cooling element? The answer is MIG welding. Okay, number 65, which of the following welding methods uses argon gas as cooling element? This is TIG welding, letter C. Number 66, which of the following welding methods that uses fuel gas combined with oxygen to produce flame? The answer is letter D. Number 67, in oxyacetylene welding, the shorter but larger diameter storage tank is for? Okay, this was the $1 million question. This is acetylene, letter B. Number 68, in oxyacetylene welding, the taller but smaller diameter storage tank is for oxygen. Number 69. 69, the full pressure of the oxygen cylinder in oxyacetylene welding is, okay, so you just have to memorize this one, 2,200 PSI. Number 70, it is a component of an oxyacetylene welding equipment used to mix the gas and the acetylene. So if we want to use, if we want to mix the acetylene and the oxygen, the device is called, okay, torch. Okay, that's letter B. Now, the hose is just simply a passageway, and then the regulator is just simply something like a valve. But the device that mixes is the torch. Okay, number 71. In oxyacetylene welding, if the mixture of oxygen is too much for the acetylene, it will provide oxidation flame. Number 72. If the mixture of acetylene is too much for the oxygen, then it will have a carbonizing flame. So it's just basically a rich and lean mixture. Now, number 73, which of the following position is not possible for shielded metal arc welding? The answer is the answer is none of the above. Letter E. Okay, number 74. Now, for number 74, The welding electrode specified to be used for a flat bed dryer project is 1/8 size E6013. Generally, what should be the amperage setting for the machine? This is just something like a rule of thumb only, but the rule of thumb is that we have 1000 amps, right, times 1/8 or times 1/8, so that's basically 125